Alright, so it's Niaki. It's a Niaki osteozone. So today we are simply going to have the discussion of the paper November 2019 chemistry from the Zimsec exam board. So we did section A, and today we are mainly focusing on section B. So if you're doing Zimsec, you need to take note of these instructions. The candidates for section A, we are required to answer all the questions, and then for section B, we are only required to answer any 4 questions, right? So here we don't mainly focus on exam board, but we try to answer as many questions as possible from different exam boards, right? So if you're doing Cambridge, you can still engage in our discussions because sodium from the Cambridge exam board is still the same sodium in the Zimsec exam board, right? So what you only need to do is to acquire data and to try to answer these questions, right? And also remember to subscribe so that you'll be notified whenever we post. We are having my tutorials in all the science subjects, both for the A levels and the O level. So we have an A level channel, which is Niaki A level, and then an O level channel, which is Niaki O level. So always remember to subscribe, right? So we are on number 6, right? So number 6 says table 6.1 is an incomplete table showing the raw materials used in the production of nitric acid, right? So this is what you call the Oswald process, right? The Oswald process. So the Oswald process is defined as the catalytic oxidation of ammonia, right? So this is the Oswald process, the catalytic oxidation of ammonia. So for on the industrial processes, we have two principles. So we want to increase yield. So this is the main agenda for all the industrial processes. We want to increase yield, and we want to cut or to reduce the costs, right? So we want to increase yield and we want to reduce other costs. So these are the factors which governs all the conditions in the industrial processes. So we have 3 main industrial processes. We have the Oswald process, we have the Haber process, the production of ammonia, and then we have the conduct process, which is the production of sulfuric acid. So we have the full topical dissection of these industrial processes on our playlist. So you should go and have a look on that topical video, so that this session will be a walkover for you, right? So I believe you guys you have already visited our topical series, so that you can easily understand these examination questions, right? So the first one requires us to give the raw materials and to give the sources, right? So for the raw materials for the Oswald process, we are simply going to have ammonia, and we are going to have oxygen, since we said it is the catalytic oxidation, meaning to say we are going to have oxidation of ammonia by oxygen. So oxidation is defined as the gain of oxygen, right? And then for the sources, ammonia is going to be from the Haber process. So we are going to have a run through of the Haber process and the conduct process, all right? And then oxygen is going to be from the fractional distillation of liquefied air, right? So we are going to have fractional distillation of liquefied air, right? So this is what you need to understand. And then the next question says states the conditions necessary for the production of ammonia, for the production of nitric acid. So we are going to have a temperature of about 800 degrees Celsius to 900 degrees Celsius, and then we are going to have a pressure of about 8 to 10 atm, and then platinum rhodium used as a catalyst. So this one is also a typical catalyst in the catalytic converters, right? Converters in the car exhaust field, right? In the car exhaust. So we must know the catalytic converter by heart. For the catalytic converters, we are going to have platinum and rhodium as the catalyst, and also palladium, right? So palladium is also a catalyst in the catalytic converter. And then we are going to have the production of nitrogen, carbon dioxide, and water. So nitrogen is produced from the nitrogen oxides, and then carbon dioxide from carbon monoxide, and then carbon monoxide and water also produced from unburnt hydrocarbons. So these are the products, these are the reactions in the catalytic converter. Are we together? So you must know the catalytic converter by heart. All right. So here we don't mainly focus on the given question. We don't mainly focus on the given question, but we try to expand the questions by answering as many concepts within that given radius, right? So The next question says, write any 3 chemical equations for the reaction. So we say it is the catalytic oxidation of ammonia, right? It is the catalytic oxidation of ammonia. So the first reaction, we are going to have the oxidation of ammonia, right? The oxidation of ammonia to give nitric oxide plus water. So nitrogen monoxide can also be called nitric oxide. You need to take note of that, right? And then we are simply going to balance this equation. So to balance this equation, we need a 4 here, and also need a 4 there, and we need a 5 here, and then we need a 6 here, right? So this equation is now balanced. And also you need to take note that this equation is not a reversible reaction. This is not a reversible reaction. So we are only going to have these conditions which favors this forward direction, right? So this is what you need to understand. And we also give the second equation. So the second equation is the oxidation of our nitric oxide. So it's NO plus oxygen. So this one is the reversible reaction, right? Are we together? To give nitrogen dioxide. So to balance this equation, we need a 2 here, and then we can have a 2 there. So this equation is a reversible reaction, meaning to say it proceeds in either direction, right? It proceeds in either direction. Are we together? So this equation is an exothermic reaction. You need also to take note of that. These are industrial processes. They are exothermic reaction. So you must have the conditions which facilitates the forward reaction, which is low temperature. And then we are going, so we can compare the number of moles of gases. So here we're having 3 moles here on this side, and then 2 here, meaning to say high pressure can increase the forward reaction, but high pressure is difficult to maintain. The cost of the pipes is difficult to maintain, so we are going to use a moderate pressure. Are we together? So this is what you need to understand. So these are all in gaseous phases. Gases, and then gases. So these are all in the gaseous phases, right? So you must understand these conditions by heart. So the last equation, we are simply going to have the produced nitrogen dioxide reacting with cold water to give, so this one is not a reversible reaction, to give nitric acid plus nitrogen monoxide, right? So to balance this equation, we are simply going to have a 2 here, and we can have a 3 there, and it is now balanced, right? So this is the production of nitric acid, right? So for you to understand conditions of the Ostwald process, you need to know this mnemonic by heart. So the mnemonic says ammonia burns hot, and then nitrogen dioxide forms when warm, and then the acid absorbs when cold, and all need little push. So this is the mnemonic you need to know for the Ostwald process. We are saying ammonia burns what, meaning to say the temperatures in this oxidation of ammonia, we have high temperatures, meaning to say it burns what. And then nitrogen dioxide is formed when warm, so we are going to have reduced temperatures of about 150 degrees Celsius here in this reversible reaction, right? And then all this, and also here we are having the acid absorbed when cold. So here we are going to have cold water here, right? So this water is cold, so meaning to say the temperature decreases as we go down the processes. And then we are going to have a little push, meaning to say we are going to have reduced pressure. Are we together? So this is what you need to know for the Ostwald process. And then for other industrial processes, like the conduct process and the Haber process, I'm simply going to give you the required. So let me clear here so that you can easily see. So for the conduct process, we are going to have the oxidation of sulfur from the sulfur containing compounds like iron pyrites and etc., right? So oxidation of sulfur to give sulfur dioxide, right? And then the conduct process is where we are having the oxidation of sulfur dioxide to give sulfur trioxide, right? So this is the conduct process. So to balance this equation, we are simply going to have a 2 here and then a 2 here, and then the conditions. So this one is an exothermic reaction, right? So all the industrial processes, the Haber process, the Ostwald, and the conduct are exothermic reactions. So the conditions here, we are going to have vanadium pentoxide is the catalyst, right, of the reaction, and then a temperature of 450 degrees Celsius, and then a pressure of 1 to 2 atm of pressure, right? So these are the conditions we are going to have, right? So from here we are simply going to have option of this sulfur trioxide by already made concentrated sulfuric acid to produce oleum, right? So we are going to have sulfur trioxide plus concentrated sulfuric acid to give oleum. So oleum H2S2O7, right? So this reaction is very, very important to avoid the production of mists. So we can have another reaction like the hydration of sulfur trioxide to give sulfuric acid. So we want to avoid this reaction. Why? Because it produces a mist of sulfuric acid, or the fumes of sulfuric acid, which are difficult to condense to give industrial sulfuric acid. So we go in this direction so that we can produce oleum, which you can then use to make sulfuric acid. Are we together? So you must know the reason why we avoid this reaction. Are we together? And then for the Haber process, so you must be able to explain this condition in terms of the Le-Chatelier's principle. So we must know that the Le-Chatelier's principle is the one which governs all the industrial processes, all the equilibrium reactions. So the Le-Chatelier's principle states that if a reaction in equilibrium is disturbed, the equilibrium will shift to oppose the change and try to reverse it, right? So we are having a reaction which is exothermic, meaning to say it produces a lot of heat, right? A lot of heat is being released to the surroundings. So if you are having an increase in temperature, if we are to increase temperature, we are going to favor this endothermic direction. So this one is the exothermic direction. So we're going to favor this endothermic direction. So endothermic direction absorbs heat. We said endothermic reactions, they absorb heat. So if you are to increase temperature, we are going to absorb the increased heat by favoring this endothermic direction. So these are the principles of the Le-Chatelier's principle you need to know. You must know this Le-Chatelier's principle by heart. Are we together, guys? So we can now move on to the Haber process, right? So we have these topical dissections in our series. So you must go and have the understanding there, right? So here we are simply going to dissect the Haber process as fast as we can, so that we can finish the rest of the paper, right? So Haber process, we're going to have the reaction between nitrogen and hydrogen to give ammonia. So Haber process is simply the production of ammonia, and to balance this equation we need a 3 here, and then we need a 2 there, and then this is exothermic. And then for the conditions, we are simply going to use temperature of about 450 degrees. So these are compromised conditions, right? And then for 200 atms the pressure, and then we're going to use a catalyst which is powdered iron. It's powdered iron, not iron. It's powdered. The iron must be powdered. So the reason, in terms of our reaction kinetics, the reason we are having powdered iron is to increase surface area for the catalyst, so that we can have the gases absorbing on the surface of the catalyst. So this one is what we call a homogeneous. This one is a heterogeneous catalysis. We are having this in gaseous phase, and then this one in the solid phase. So they are in different phases. So they are hetero, meaning different phases, right? So it's a heterogeneous catalysis. So we are simply going to have nitrogen and hydrogen here, and then iron here. So it's powdered, meaning to say we are going to have a lot of contact points, right? So they can absorb on the surface, on increased surface area, right? And then if you are to have marbles or lumps of iron, we are simply going to have these hydrogen atoms. They are going to absorb only on the peripherals, on the outer surfaces. So the iron particles within the inner particles, they are not in the catalysis. They are not part of the catalysis, right? So we are having a reduced surface area. So you must understand this in terms of reaction kinetics or chemical kinetics. Are we together? So this is what you need to know. And we are having, so for our process, we are going to have a 15% yield. So the yield is 15%. And the reactants are recycled so that we can maximize yield. So we said the reason or the agenda behind all these industrial processes is to increase yield. We are to increase yield and to cut the costs. Are we together? So these are the reasons, or these are the agendas behind all these industrial processes. And also you should appreciate the uses of sulfuric acid, the uses of ammonia, the uses of nitric acid, and you are good to go for all the industrial processes. And then the sources of nitrogen the sources of nitrogen, we are going to obtain nitrogen from fractional distillation of liquefied air from air, right? And we can have hydrogen from the steam reforming of nitrogen, natural gas, I mean. We can have steam reforming of natural gas, which is methane. So you must also appreciate, you must know the effects of this reaction, that it produces carbon monoxide, which is a toxic gas. Are we together? And we can now safely proceed to the next part, which says calculate the oxidation state of sulfur in hydrogen sulfide and sulfuric acid. So we can say hydrogen sulfide and then X for sulfur, and then here is +1. So hydrogen is treated as a metal, so it's +1, except in the hydrides where hydrogen is bonded to the group 1 metals, right? Plus X, they are known to give 0. So it's 2 plus X is equal to 0, and then X is equal to -2. So this one is a simple linear equation. So X is equal to -2. And then for sulfuric acid, we're having SO4. So it's +1 here, and then X here, and then -2 here. So we're simply going to say +1, how many? By 2, plus X, and then here -2, how many? 4. So we're simply going to have 2 plus X minus 8 to equal to 0, and then X is equal to X -6 is equal to 0, and then X is equal to plus 6. Are we together? So the oxidation state, X is equal to +6. As simple as that. And then the other question says write the chemical formula for ammonium nitrate. So we are simply going to deduce the ions in question. So you have the ammonium ion and the nitrate ion. So these two, we are simply going to interchange the coefficients of these charges. So here is 1, and then there is 1. So it's NH4NO3, and we are done. Are we together? So this is what you need to understand. And then the next question says write the chemical formula of ammonium nitrate, and then this one again, ammonium nitrate. All right, so name the 3 types of bonds in ammonium nitrate. So ammonium nitrate, so this one is a very, very difficult question for you guys. So we are having so in terms of charges, so this one is an ionic bond. We are having this cation and then this polyvalent anion, right? So automatically this one becomes an ionic compound, the first one. And then the bonds within these nitrate ion, and then these related with this nitrate ion. So the bond within this nitrate ion, it is the covalent bonding, right? Covalent bonding. And then the bond within this ammonium ion. So ammonium ion is formed by the hydrogenation, the protonation of ammonia. You're going to add a proton to ammonia to give ammonium ion. So the bond in ammonia, it's a covalent bond. So this is what we call dative bonding, when we are to add this proton, right? So we can draw the structure of ammonia so that you can understand, right? So nitrogen, then these 3 hydrogens. So this is the hydrogen, right? The dot and cross, right? And then we are left with 2 electrons. So this nitrogen is in group 5. Right? So we are left with these 2 electrons, and then the proton, hydrogen has got 1 electron. So if we are having this plus, meaning to say we have lost this 1 electron, so meaning to say nitrogen doesn't have any electron, right? So hydrogen is coming to bonding without an electron, so it is bonding directly to these electrons here to form what you call the dative bond. So another bond we are having here is a dative bond. So a dative bond is a subgroup or subtype of a covalent bond. So the properties are the same. Once a dative bond is formed, it is very, very similar to a covalent bond. It is very, very identical to a covalent bond. Are we together? So this is what you need to understand here. And then we can now proceed to number 7. So number 7 says fig 7.1 shows a reaction between the reaction of barium and some of its compound. So we are having barium here, and then heat gently in air to have L. So barium plus A, we are simply going to have barium oxide. And then from L to M, we have aqueous here. So meaning to say this the hydration of barium oxide to give barium hydroxide. Are we together? So these are the chemical formulas. So I taught you guys how to write these chemical formulas, right? So if you go to our playlist, our topical playlist, these revisions, these papers are going to be a walkover thing for you. Are we together? And then here we're having the reaction between barium hydroxide and sulfuric acid. So we are simply going to have so let us write the equations so that you guys, so it's barium plus oxygen, the first equation, So this is going to give us barium oxide, right? So we can simply balance by having a 2 here and then a 2 there, right? And then the other equation, we're having barium oxide plus water to give us barium hydroxide, right, plus hydrogen gas, we can say. So to balance this equation, we are simply going to have a 2 here, right? This is the equation. And then for the reaction between barium hydroxide and sulfuric acid, barium hydroxide plus sulfuric acid, we're simply going, so this one is a neutralization reaction between an alkali and an acid, right? So this one is a neutralization reaction. So you must know the ionic equation for the neutralization reaction is the proton plus the hydroxyl ion to give water. So this is the ionic equation for all neutralization reaction, right? So at times they can say we are reacting in acidic medium M plus a basic medium Z, right? The ionic equation, this one is universal for all the neutralization reaction. Are we together? So here we are simply going to have barium sulfate plus water. So this equation, to balance this one, we can have a 2 here, right? And the equation is now balanced, right? The equation is now balanced. Are we together? So this is what you need to understand. The equation says M, and then we are going to bubble carbon dioxide, and then we are going to have Y. So Y is in aqueous form. So we were supposed to have the reaction between barium hydroxide plus carbon dioxide to give barium carbonate, but you are having in aqueous. Barium carbonate is insoluble. All the carbonates are insoluble except those of group 1 and the ammonium, right? So all the carbonates are insoluble except group 1 and ammonium carbonate. So these are the only soluble ones. So barium carbonate is insoluble. So here we can't have barium carbonate because of this aqueous phase. So we are simply going to have barium hydrogen carbonate. Are we together? So this is the equation. So to balance this equation, we need a 2 here. We need a 2 there. The equation is now balanced, right? So the question says identify the compound L, M, X, and L. So we said L is barium oxide, right? M is barium oxide. And then we have M, which is barium hydroxide. And then we have X. X is barium sulfate. Are we together? And then for L, it's barium hydrogen carbonate. Barium hydrogen carbonate. Are we together? So these are the compounds we are having, and then awarded for 4 marks. And then write a balanced equation for the formation of M, X, and L. So for M, formation of M, so this is the equation. And then for the formation of so these are the equations, right? So these are the equations for all these processes, right? So we have already done that. And then the next question says write a balanced chemical equation for the reaction between magnesium and steam. So magnesium and steam, the reaction is vigorous and it is going to give us magnesium oxide. But if you are having cold water, we are going to have magnesium hydroxide. So for steam, we have to have oxide, and then with cold water, hydroxide. You need to take note of that, right? So we are going to have magnesium plus steam to give us magnesium oxide plus hydrogen gas. So these are the equations, and then here steam in form of gas, and then here solid. So to balance this equation is balanced, right? And then the next question says a mass of 1.32 grams of carbon dioxide was collected when a sample of calcium carbonate was heated. So we said M carbonate heated will give M oxide plus carbon dioxide. So this is the equation for all the decomposition of the thermal decomposition of the carbonates. Are we together? So here we are given the decomposition of calcium carbonate, so we are simply replacing M with calcium. So it's M, as simple as that. Are we together? We have another one for the decomposition of nitrates. So for nitrates, we are simply going to have the metal oxide nitrogen dioxide and oxygen, right? So we are going to have metal oxide plus nitrogen dioxide plus oxygen for all the thermal decomposition of metal nitrates, the divalent, the group 2 metal nitrates. Are we together? So to balance this equation, we are simply going to have a 2 here, and to have a 4 there, and then a 2 here. Yeah, and the equation is balanced. So this is what you need to know for all the thermal decomposition of the nitrates and the carbonates for the group 2 elements, right? The divalent metal cations, right? So here we're given that, so let me clear this part, right, so that you can easily understand the questions. So here we are given that 1.2 grams of carbon dioxide was collected when we heated this calcium carbonate. So we are required to calculate the mass of calcium carbonate that was heated. So according to these molecular ratios, the MR of calcium carbonate is 100. Are we together? So the MR of calcium carbonate is 100. So we're simply going to add 40 plus 12 plus 16 by 3. So this will obviously give us 100. So 100 is producing 44. So here we are having 44. The MR of carbon dioxide. So it's 44. So 1 will give us 100 will give us 44, right? So what are we going to use so that we can give a yield of 1.32 grams? So we are going to use less, right? So we are going to use less. So we are simply going to say 100 by 132 over 44 and punch this straight to our calculator. So it's 1.32 divided by 44 multiplied by 100, and this will give us 3. So we're going to have 3 grams. Are we together? So we now move on to the next part, which says state any 3 uses of calcium oxide. So calcium oxide is also called quick lime, and we have slacked lime. So slacked lime, it is calcium hydroxide in paste form, right? And then we have lime water, which is calcium hydroxide in aqueous form, which is lime water. And then this one slacked lime, right? So when they say lime, they are referring to these compounds, right? So we are given the question which says state any 3 uses of calcium oxide. So the uses, we are simply going to use this one in the blast furnace as a flask to remove impurity. So the calcium carbonate, the limestone is added, and then we have that thermal decomposition in this reaction, right? So this is limestone, the chemical formula of limestone. So this will produce quick lime, which will then react with silica or silicon dioxide in the blast furnace to form slag, which is calcium silicate. Are we together? So silica is equal to silicon dioxide, right? And then we can use it in the manufacturing of cement to make cement, and also we can use it to neutralize acidic soils, neutralizing acidic soils, right? And then we can use it in the treatment of water, water treatment, the glass making, the manufacturing of glass, and etc. And also glass manufacturing, right? And we are done. So we can proceed to the next question, which is number 8, right? So number 8 says a hydrocarbon X consists of 86% carbon and then 14% hydrogen, and then the relative molecular mass of X is 56, right? So we are required to deduce the molecular formula of X. So this is awarded for 5 marks. So first we need to deduce the empirical formula. So we defined molecular formula as the multiple of the empirical formula. So empirical formula is defined as the simplest whole number ratio of atoms present within a compound, right? The simplest whole number ratio. It's a whole number ratio. It is not just a ratio, it's a whole number ratio of atoms present within a compound. So here we start by highlighting the atoms in question and then the percentage occurrence. So we're having 86, and then here we're having 14, and then we're going to divide with AR. So to divide with the AR of carbon, which is 12, and then that one of hydrogen, which is 1. So we're simply going straight to our calculator. So straight to our calculator, we're going to have 86 divided by 12. We're going to have 7.1667, right? So this is the number of moles here, and then here we're going to have 14, right? and then we divide with the smallest again. We divide again with the smallest. We divide with the smallest. This one is the smallest, 7.1667, and then here 7.1667. Are we together? So here we're simply going to have 1, and then this one we go straight to our calculator, and we are going to have 1.253 and etc. So we say it from the definition, it is a whole number ratio, meaning to say we want to round to the nearest whole number, right? So we're going to have 1 and then 2 here. Are we together? So the simplest ratio is CH2. So this is the empirical formula. And we said molecular formula, it is the multiple of the empirical formula, meaning to say empirical formula multiplied by X will give us the molecular formula. We need a certain integer which will then will multiply with the empirical formula for us to obtain the molecular formula. So we are having this empirical formula, so we can do the same, right? So we can multiply the empirical mass with X, and then we can still have the molecular mass, right? So our empirical mass, empirical mass is 12 plus 2 to give us 14. So this is the empirical mass. So it's X by the empirical mass, 14 is equal to the molecular mass, which is 56, right? So we go straight to the linear equations, mathematical approach, and then we're going to divide by 14 divided by 14. So 56 divided by 14, we're going to have 4. So our X is equal to 4. So we can now use the equation which says empirical formula is equal to by X is equal to molecular formula. So the value of X, we say X is equal to 4. So it's 4 by empirical formula, CH2 is equal to molecular formula. So we multiply by 4, so it's C4 and then H8 is the molecular formula, and we are done. So it is awarded for 5 marks. Are we together? So this is simple stuff, right? So the question says, state with the reason the homologous series to which X belongs. So we can deduce the homologous series by simply applying the general formula. So the general formula here is Cn, and then so H to N, right? As you can see, N is 4 and then 2N is 8. So this is Cn to N. So this one is in our alkene, right? So this one belongs to the alkene homologous series. So homologous series is defined as a family of organic compounds with the same general formula, right? So they have the same general formula, they have the same functional group, and then similar chemical reactions and similar chemical properties. Are we together? So you must be able to define these terms with respect to organic chemistry. So you should be able to define the functional group, esterification, hydrocarbons, what else? Isomerism, right? And etc. And so you must go and have a look on our topical series. And then the next question says, describe a chemical test that can be used to show the presence of X. So these are what you call the follow-up questions. So if you got this wrong, obviously you're going to have this one also wrong. So to confirm the presence of an alkene, we are going to use bromine in the darkness, right? So bromine is decolorized, right? Decolorized. So the color of bromine, it is an orange liquid. We can use bromine gas, which is a reddish brown gas. So you must highlight that we are using darkness as a condition, because in the presence of UV light, an alkane can also decolorize bromine in a reaction what you call the free radical substitution. So here we are simply going to have the bromine double bond undergoing what you call the homolytic fusion to form the free radicals of bromine, which will then react with the alkene, right? So which will then react with the alkane. So alkanes can also decolorize bromine water in the presence of light. So we must highlight that we are using darkness, because in darkness alkane cannot decolorize bromine water. Are we together? So this is what you need to understand. And then we now proceed to the next question. So the next question says, Table 8.1 is an incomplete table showing the alloys of copper and their composition. So complete the table by naming 2 alloys of copper. So we have brass and then we have bronze. So brass is equal to bra-cos, and then bronze is broco-tin. So here we have cos, so it's copper, and zinc, and then copper and tin. As simple as that. Are we together, guys? So this is what you need to understand. And then we can now safely proceed to the next question. So the next question says, describe the biological importance of iron, and describe the industrial importance of iron. So the biological importance of iron, it is used in the manufacturing of hemoglobin, and also myoglobin, and also in the manufacturing of enzyme cofactors. So this is biology, right? Enzyme cofactors, and also in the manufacturing of neurotransmitters, in the boosting of the immune system, right? Immune system. These are the biological importance of iron. And also for the industrial importance, we're going to use it in the construction and infrastructure, right? We can also use it to make car bodies and engines, and we can use it to make tools, and making shipping, buildings, and railway. We can use it to make magnets, right? And pipes, gas pipes, right? So we need to highlight that, gas pipes, right? So these are the uses of iron. And then we proceed to number 9. So number 9 says, explain what is meant by the term hydrocarbon. So hydrocarbon is an organic compound. So the definition must include this organic compound which contains hydrogen and carbon only. So you must underline these. They are very, very important in your definition. We are having an organic compound containing hydrogen and carbon only, and it is awarded for 2 marks. So the next question says, name the process by which alkanes are obtained from petroleum. So we are simply going to have cracking. So you must know cracking inside out. So cracking is defined as the process. It is a process of breaking down large hydrocarbon molecules into smaller, more useful molecules, right? So we are simply going to obtain alkene from this cracking, and also hydrogen. So the main products, we are breaking large molecular alkanes into either in alkene of a low or smaller molecular size or mass, or in alkene or hydrogen gas. So we have 2 types of cracking. We have thermal cracking and catalytic cracking, right? So we must understand this. We have thermal cracking. So thermal cracking, the conditions, we're going to use high pressure in the temperature of 700 to 900 degrees Celsius, right? So we have another one which is catalytic cracking, right? So catalytic cracking, we're going to use a temperature of 450 degrees Celsius, and we're going to use a catalyst, since it is called catalytic, right? We're going to use a catalyst, aluminum oxide, or the you can say the zeolite oxide. So these are the conditions for catalytic cracking, right? Here also we can say fractional distillation, right? We can also have a fractional distillation, right? We can also have fractional distillation as the answer to this question. So we are going to use cracking and fractional distillation to be more specific. So this one will produce the exact needed alkane, and this one will give a range of products. So we are going to have so you need to understand, you need to know the list of the products of fractional distillation. So fractional distillation, we are using the principles of distillation, separating based on their different boiling points, right? So we are starting with the gases, and then we go on to gasoline, which is petrol, and then naphtha, and then kerosene, which is paraffin, and then we go on to diesel, and then we go on to wax or lubricating oil, and then lastly we have bitumen, right? So this is the order and then we are going to have, this one is the residue, right? This is the last two to distill, right? And then this one is the first, second, third, and etc. So this is fractional distillation, right? And now we can move to the next part of the question, which says draw the structure of any three possible isomers of an alkane with 6 carbon atoms. So 6 with carbon atom is hexene, right? So we are using hexene, right? So we're simply going to have the isomers of hexene, right? So the isomers of hexene, so we're simply going to draw this H3, H, and then H, 1, 2, 3, 4, H, 5, and we are done with the first one, which is the straight chain, right? So how many carbon atoms? 1, 2, 3, 4, 5, 6, right? And then we go on to the next one. So we can draw 2-methylpentane, right? So it's 2-methylpentane, right? So this one, now we're simply going to say H here, H there, and then C. So we said it's 2-methyl, so 2 here, H, the methyl group, and we can proceed to draw the 1, 2, 3, 4, 5, and we are done. Are we together? We are done with the other one, and then we can draw 3-methylpentane again, right? So it's 3-methylpentane, right? So we're shifting this methyl group to the third hydrocarbon atom, as simple as that. So we are simply swapping, and we are done, right? And then we can now proceed to the next part, which says write a chemical equation for the combustion of propane. So for the combustion of all the hydrocarbons, we use this formula. So it's X plus Y over 4 oxygen plus to give. So this is going to give us X moles of carbon dioxide plus Y over 2 moles of water, right? So we can apply this one using propane, right? So propane is an alkane. So alkane, the general formula is CnH2n plus 2. So prop means 3. So we're going to have C3, and then by 2 to give 2n is 6 plus 2, 8. 8 here, right? So plus, we said oxygen. So this one is complete combustion, meaning to say you're going to produce carbon dioxide plus water. And then we say the number of moles for oxygen gas, we are simply going to say X, right? So it's 3 plus Y, is or Y 8 over 4 over 4. So it's 3 plus 2 to give us 5. So this is how you balance these organic reactions. And then here the number of moles of carbon dioxide is X. So our X here is 3. So you're going to have 3 here. And then the number of moles for water is Y over 2. Our Y is equal to 8. So 8 over 2, we're going to have 4. And then the equation is balanced. Simple as that. And then we can now proceed to the next part. So the next part says methane reacts with chlorine in the presence of UV light, right? So draw the structural formula for the organic compound formed. So this is what you call the free radical substitution reaction. So we said this reaction is very, very important. This reaction is very, very important. So we're going to have chlorine to chlorine double bond is the initiation reaction. So we're going to break this bond using UV in a reaction called homolytic fission. So homo meaning to say the same. So we're going to produce the same radicals, right? So this one is going to take 1 electron, and then this one to take 1 electron. So for O level, these equations are not necessary for you, but I'm just showing you these equations so that you can have the better understanding, right? To produce 2 chlorine radicals. So these radicals are the ones which are going, these radicals are very, very reactive. So they are the ones which are going to react with methane. So you're going to have C4 plus the radical to give us CH3Cl, right? So this is the radical plus hydrogen chloride. So this is the reaction we are simply going to have. Are we together? So we have this reaction in stages. We have this initiation stage, the propagation stage, and then the termination stage. So we are not going to discuss this we are not going to discuss that during this session. We are going to talk much of it when we are doing A-level chemistry. For now, just appreciate it in this way, right? So we are going to have this chloromethane. So the formula, the structural formula, this is the structural formula. So it's C H H and then Cl, and we are done, right? So we can now proceed to the equation which says name this type of reaction. So we say this one is a free radical substitution reaction, right? And then the next part says ethanol is an organic compound that can be used to produce ethene and to produce ethanoic acid. So the reaction from ethene to ethanol is called hydration. We are going to have hydration, and then from ethanol to ethene it's dehydration, right? From ethanol to ethanoic acid is called oxidation reaction, right? So this is what you need to understand when dealing with this kind of question. So the conditions are for the hydration and the dehydration. So for the hydration, we are simply going to have concentrated phosphoric acid at a temperature of 300 degrees Celsius at a pressure of 60 to 70 atm. And then for the dehydration method, we are simply going to have concentrated sulfuric acid or aluminium oxide as the catalyst at a temperature of 170 degrees Celsius, right? So these are the conditions we are going to have. So name the reagent. So we are going to have the reagent of reaction X. So the reaction X is a dehydration. So we're having concentrated sulfuric acid, right? So the reagent for the reaction Y, we are simply going to have acidified potassium dichromate or potassium permanganate, right? So acidified potassium dichromate or potassium permanganate, right? And we are done. So this is what you need to know. And then here we're going to have concentrated sulfuric acid for the dehydration, and we are done. And then so this one can also be called an elimination reaction, right? So you need also to understand that. So state 1, use of ethanol. So ethanol can be used as a fuel, can be used as a solvent in paints, varnish inks, and also of medical importance, and also for alcoholic beverages, and also as an antiseptic. So we use ethanol as an antiseptic. You must understand that. All right. And then draw one repeat unit of polyethylene. So we start with ethene. So this is the ethene, the monomer, right? And then for the repeat unit, you are simply breaking up this double bond, carbon to carbon double bond, right? And the Fn. So this is the repeat unit. Are we together? And then the next question says draw a block diagram to show the structure of terylene. So terylene is an ester polymer. It's a polyester with the ester linkage, right? So we're simply going to use, so they say block polymer, right? Block diagram. So we're simply going to draw these monomers for you to understand, right? So these are the monomers, and then we have the other one shaded so that we can easily differentiate the two, right? So for polymerization, we are removing this group to form water, right? And we are left with these two reacting. So this is the ester linkage, right? This is the ester linkage. So we are simply going to have C double bond here, or from this group. Then we are going to shade here, and then it goes. So it's terylene, you must highlight that, right? And then we do the same here. We're going to have C, right? And then it goes on. So this is the polymer, right? This is the polymer, and this one is what you call the ester linkage, right? And also you must take note of nylon with the amide linkage, and also the proteins. So the nylon and the proteins, they have the amide linkage, and then terylene and lipids, they have this ester linkage. Are we together? So this is what you need to understand. So for nylon, we are simply going to have this amine, so amine, and then we're going to have N, and then H here, and then N, and then H, and then H, and we're simply going to eliminate this, and we are done. Are we together? So we can now move on to the next part, which is number 10. Number 10 says, name a suitable method of disposing metallic waste, bones from a canteen and tree leaves. So metallic waste, we can use recycling, right? So recycling is the most suitable method, right? And we can also reuse in the manufacturing. And then bones, we can compost. So we have composting, right, of the bones. So since bones are organic, they are going to decompose, right, with time. And then for tree leaves, we can also use composting, right? And we are done. So the question says, describe the challenges associated with disposal of plastic waste. So plastics, they are non-biodegradable, right? And also they cause environmental pollution, right? Environmental pollution, also they can have recycling challenges, and etc., right? So these are the effects, and we can now proceed to number B. So number B says table 10.1 is an incomplete table showing some of the pollutants, their sources, and their effects on the environment, right? So complete the table by stating the source of the named pollutant and its effect on the environment. So here is the table. We are having carbon monoxide, and then we are also having the oxides of nitrogen. So the sources of carbon monoxide, it is the incomplete combustion of fossil fuels, incomplete combustion of fossil fuels, right? And then that one of oxides of nitrogen, so we are going to have high temperature combustion in vehicles and power plants. So we have power plants and high temperature combustion in vehicles. So you choose one, right? And then the environmental, so they say environmental effects, right? So you must take note of that. So they contribute, so carbon monoxide contribute to smoke formation, photochemical smoke formation. And then this one also contribute to acid rain. So you must understand that we are having environmental problems, so we can then include other biological problems, biological effects, like carbon monoxide affecting the hemoglobin within the human blood system, forming what you call carboxyhemoglobin, and then nitrogen oxides affecting the respiratory systems, right? So the next question says, describe how the release of oxides of nitrogen in the atmosphere can be minimized. So we can minimize this by using catalytic converters, right? Catalytic converters in the vehicle. So catalytic converters, they are going to reduce these oxides of nitrogen into nitrogen gas, right? So this is the reaction. And also we can improve the combustion efficiency in the fuel engine and use low nitrogen containing fuels, right? And improve the efficiency of the combustion in the engines, right? And then the next question says, describe the causes of low pH in soils. So describe the causes of acidic soils. That's the question, right? So acidic soils, it is caused mainly by acid rain, right? So we are having acid rain from caused by emission of sulfur dioxide and nitrogen oxides from the industries. So this will then hydrate to form here we're going to have sulfurous acid or sulfuric acid. We are going to have nitrous acid or nitric acid. So these acids they will then pollute the ecosystem through acidification, right? So this is what you need to understand. And also decomposition of some organic matter. So decomposition of some organic matter can lead to the acidification of soil, and we are done. And then we now move on to the next part, which says write a balanced chemical equation to show how lime adjusts acidic soils, right? So lime, it's either calcium oxide or calcium hydroxide. So it's calcium hydroxide plus the acidic medium, which is the proton, to give calcium true ion of that salt, plus water. And to balance this equation, we're simply going to have a 2 here and then a 2 there. The equation is balanced, right? And then we now move on to the next part, and we are done with this paper, right?